students. So to start off, I want you to think about the following questions. Are gases, like the gases in air, matter?
Yes, the air around us is made up of different gases like oxygen and carbon dioxide. They're just molecules that are spread very far apart, much like that in a liquid or solid. Since the molecules of a gas have mass and take up space, is gas matter? Yes.
I think I get it. Although I think people might be a little confused about gas having mass. Does a balloon get lighter when you blow it up? So let's take a look. I conveniently have at home my triple beam balance. Of course I do. So I also have a balloon. And I tried this earlier and the balloon got really staticky. Remember the whole balloon staticky thing that we did before when we studied static? So I'm going to put my cup on here so that I'm going to measure, so I can balance my balloon on the cup. So the first thing I have to do is I have to see how much my balloon with no air, the mass, what's the mass of my balloon with no air. So the first thing I'm going to do is I'm going to put that in. I didn't show you, but I did make sure that it was at 0 before. And then again, when we use the triple beam balance, remember how we learned how to use the biggest rider first, and we move the biggest rider down until it drops. And then we back it up 1. It's hard doing it backwards. And then we use the tens rider. So it starts to go down. Then we use the 1s. Okay, so apparently I can't do it backwards, but it's okay. I can do it this way. It'll be okay. So I can measure the mass of the balloon in the cup with no air in it. So can you read what that says? It is 150.8 grams. So let me just write that down. 150.8 grams. And the arrow is lined up exactly. So now what do I need to do? Now I'm going to blow up. I'm going to put some air in the balloon. Ready? So now what's the difference between what I just did and this? So the difference is I have the same cup, I have the same balloon, and I have the same, and what is going to happen as I put the balloon gently here? What happens? Whoops. All staticky again. Okay, there we go. Okay, so now what do you notice? Well, now the mass of the balloon has clearly increased because now the arrow is going up. So I can measure the mass of the balloon now with the cup. And now it is, looks like 151.3 grams. So is that what it looks like to you guys?
I think so.
So if I do 151.3 minus 150.8, I notice the difference, and difference means subtract, right? The difference is 0.5 grams. So now we can clearly see that the mass of the air inside this balloon is 0.5 grams because the mass has gone up.
Let's also look at this demonstration of a deflated basketball. At the beginning, the deflated basketball has a mass of 576 grams. After inflating it, the mass increases Now it increased, after we inflated it, it increased to 581 grams. Now let's observe this can of compressed gas. What will happen to the mass after you squeeze the trigger? At the start, it's 135 grams. Now let's spray it and see what the total mass is. Okay, so now we weighed it after we sprayed it, and it's 132 grams. There we go. Okay, thank you, Miss Messina.
All right, so gases have mass. Therefore, they are matter.
So now we know that gases have mass and are matter. Let's observe how they move on a molecular level. In this animation, we can see that gas molecules are not attracted to each other. So let's take a look. So let's take a look at these gas molecules, and we can see that they're not attracted to each other. They bounce off each other, and they're very spread apart. They're really going fast, aren't they?
So in this demonstration, you will need plastic cups, a plastic bottle, detergent solution, hot water, and cold water. If you don't have these materials, just please follow along with us.
So we've been talking about whether gas is matter and whether gas molecules move the way that solid and liquid molecules do as they heat up and as they cool down. So that's what this demonstration is going to go over.
So today I have for you just a little dish detergent with some water in it. I have just a bottle, and I have a cup of very cold water and a cup of hot water. So this is the hot and this is the cold. So what I'm going to do is I'm going to take the bottle and I'm going to dip the opening so the detergent just covers the rim. So we have like a little film of detergent over the rim. Okay, now I'm going to place the bottle into the hot water. So what's inside this bottle right now is air. I'm going to put the bottle inside the hot water. Watch what happens. Can you see what's happening to the bubble? Can you tell or not?
It popped.
Yeah, I saw it.
So it popped. Why do you think it popped? Did you see that it swelled up first before it popped? So what was it? What's inside the bottle right now? There's air inside the bottle, and as we put the bottle into the hot water, what happens to that air? So air is a gas. And you can see that the hot water, oh,
It popped again.
There's our pop.
Wow.
yeah.
Wow.
So let me cool that down for a minute because I want to show you what's going to happen. So if I have the bubble and the bubble swells up again, what do you think I could do to make the bubble flatten back out again before it pops?
Heating makes the gas molecules spread out, so cooling will make the gas molecules move closer, and that should make the bubble go down.
Okay, so here we have the bubble getting bigger. I don't know, can you see it?
A little bit.
So if I put it in the cold water, what's going to happen to the bubble? Oh, look at that. Can you see how it's like sucked right in?
Oh, wow.
Why is that happening? Do you see how the film is sucked right in now?
I can a little bit.
A little bit, yeah.
You can?
Yes.
Yeah.
It all went on the inside.
And now if I make it hot again, what do you think is going to happen? Do you think those gas particles are moving apart again? Look at that. That's so cool. So if you have a chance to do this at home, you really should try, because I'm sure you all have dish detergent and hot and cold water. And you can use any kind of bottle. I happen to have this because that's what I have. But if you have a soda can or a soda bottle, anything like that, it would be fine.
Let's look at this animation. Placed in hot water, the molecules move faster and spread out. Placed in cold water, the molecules move slower and closer.
And the red arrows show you what is happening with the bubble.
That's a really great animation. So now we know that heating makes molecules move faster and farther apart. Cooling makes molecules move slower and closer together. Let's look at another animation to see how the molecules behave in each phase: solid, liquid, and gas.
So all of these samples that you're going to see here are shown at room temperature. So first we can see that in a solid, the molecules are very attracted to each other. They're vibrating, and they don't move past each other. So this gives a solid its definite shape and volume. In a liquid, we can see that the molecules are still attracted to each other, but here they're able to move past each other. We have a definite volume with liquids, but no definite shape. And then finally, in a gas, we can see that the molecules are very much not attracted to each other. They move very fast, they move freely past each other, and they have no definite shape or volume. And you can also see just how very far apart these molecules are.
So please go ahead and answer the questions in your PDF. These are due on Thursday. Thank you, everyone. Have a great day.
Bye.
Bye, guys.
Bye.